This video will discuss some useful properties of Hermitian matrices. Hermitian matrices are going to be important because operators in quantum mechanics are going to be represented as Hermitian matrices, and Hermitian matrices have some special properties which are useful, which make them especially suited to be those operators. Okay, so as defined in a previous video, the definition of a Hermitian matrix is that the adjoint of the matrix equals itself. So the elements of the adjoint matrix, so A dagger ij, equals AJI star. So you flip the indices and you take the complex conjugate. So you're taking the transpose and complex conjugate of your elements, then you're getting a Hermitian matrix. All right, if we have, let's say we have a matrix operator O, which is an n by n matrix and is Hermitian. So this has two very important properties that are going to be useful to us in quantum mechanics and electronic structure theory. Number one, it's going to have n eigenvalues, which are all real. They're going to be real numbers. So let's quickly prove this. So if we have the operator O acting on a vector alpha equals a scalar constant omega alpha times the vector alpha. Operator times vector equals constant times vector. That is the definition of being an eigenvector. So alpha is an eigenvector of O, and omega alpha is its eigenvalue. So if we take the adjoint of both sides here, the adjoint of O alpha is alpha dagger O dagger. The adjoint of omega alpha alpha is omega alpha star alpha dagger. All right, so then we know that, I think I just rewrote that here. Oh, since the operator is equal to its own adjoint, we can take O dagger and make it O again. And then we can multiply everything by alpha. So we're going to have alpha dagger O alpha, omega alpha star alpha dagger alpha. All right, so far so good. But we know that O acting on alpha equals omega alpha alpha. So this O alpha gives us omega alpha, and then omega is a constant, so we can factor it out. So we get omega alpha dagger alpha equals omega star alpha dagger alpha. The alpha dagger alpha is a constant, is a number, so we can divide both sides by whatever that number is. And then we get, as a result, that omega star equals omega. If you equal your own complex conjugate, that means your imaginary part has to be 0. So if you equal your own complex conjugate, you are by definition a real number. So all this worked in general for all eigenvectors and all eigenvalues. So if you have a Hermitian operator or a Hermitian matrix, all of your eigenvalues are going to be real, from eigenvalue 1 up to eigenvalue n. All right, second useful property of Hermitian matrices is that the eigenvectors are going to be orthogonal. So if we have O acting on beta equals omega beta, also definition of being an eigenvector and the eigenvalue associated with that eigenvector. Similarly, take the adjoint of both sides, B dagger O dagger equals omega B dagger. And since we know that omega B beta star equals omega beta, I've substituted in omega here. So I've taken its complex conjugate since those are equal. All right, once again, I'm going to multiply by alpha. So B dagger O dagger alpha equals omega beta B dagger alpha. All right, so what is omega acting on alpha? Well, what is O acting on alpha? That's omega alpha. So now we have beta dagger omega alpha. Omega is a constant. I can factor it out. So now I have omega alpha beta dagger alpha equals omega beta dagger alpha. So once again, I can move things to the same side. Omega alpha minus omega beta times beta dagger alpha equals 0. And this is true for all beta and for all alpha. So if omega alpha is not equal to omega beta, then something else has to be 0. So beta dagger times alpha is equal to a number. omega alpha minus omega beta is equal to a number, one of those numbers has to be 0 for this to be true. So if omega alpha is not omega beta, then beta dagger alpha has to equal 0. But note from previous videos that this is equal to the overlap of eigenvector B with eigenvector A. It's equal to their dot product, or the dot product of the complex conjugate of B. So beta, the dot product or scalar product, inner product of beta and alpha is equal to 0 if the eigenvalues are not equal. So that means that they are orthogonal. Similarly, you can also show that in general our eigenvectors are going to be normalized, so the inner product of them with themselves is going to be 1. So if they're orthogonal and normalized, that means that our eigenvectors are going to be orthonormal. Okay, also a useful property of Hermitian matrices to notice is that since the adjoint equals itself, alpha dagger ij equals alpha ji star, if I equals j, then this means that aii has to equal aii star. So similarly, our diagonal elements have to be real as well. So for our Hermitian matrices, as we look down the diagonal, it's if we have a set of A and a set of B numbers that are all real numbers representing the complex numbers in general, we have, as we go across the diagonal, you have the complex conjugate and of the number, and as on the diagonal we have a number which has to be real. And that's no coincidence as well, because the sum of the diagonal is the trace. The trace is equal to the sum of the diagonal. It's also equal to the sum of the eigenvalues. So if the eigenvalues have to be real, then all of the values along the diagonal have to be real as well. So these are going to be very useful properties for us in quantum mechanics, because in quantum mechanics, things that we can measure, things like energy, momentum, position, are going to be eigenvalues of Hermitian operators. So the things that we can measure, measurable properties, should be real numbers. So giving us real eigenvalues is going to be very useful. And the orthogonal eigenvectors part will become apparent in time why that's important as well. But both of these properties of Hermitian matrices, that their eigenvalues are real and eigenvectors are orthogonal, are going to come in very handy to us as we go through advanced quantum mechanics and electronic structure theory.